maybe they were looking forward to the zombie apocalypse when the cell phone towers would be down and electricity would no longer be a thing, in which case
I suppose
doing the arithmetic will be good. All right. Let's get started here. I tried to save paper by printing two pages to a side, so please forgive me if it's like way too cramped for you if you like to write big or whatever kind of thing, but just trying to save paper. All right, make it easier. You don't have to staple it or anything like that. It's all together. So exponential word problems, we're going to be dealing with a couple today. So first one, all right, we're looking at is compound interest. Okay, we're talking about interest that is compounded n times per year. All right, and the formula for this is going to be A equals P times 1 plus R over N raised to the NT power. Okay?
1 plus
1 plus R over N raised to the NT power. Okay? So this is the typical kind of situation that you would have when you put money into a savings account at a bank or something like that. Some checking accounts even carry some interest and stuff like that. But the idea is, right, that the bank, to thank you, I guess, or to reward you for allowing it to hold on to your money and use your money to then give loans out to other people, they give you a little bit of money for holding on to your money kind of thing. So, right, the interest then is just that little bit of money that's added on every so often, right? So the n times per year, that determines, well, they might do that. They might add the interest on, a certain number of times per year. I think for my savings account, I think it's every month. They do it so monthly kind of thing. You get a little, hit to your a little boost to your account there from having money in the account. Yes, Jeff.
Well, simple interest is uncommon in banking. That sometimes some accounts will have continuous interest,
right?
Which is a different equation that
we're going to be getting that next.
Which is technically every second, all the time.
Right, continuously, yes, instantaneous, yes.
It doesn't. It's not actually that much bigger. It actually grows a little bit slower than just regular compound interest.
Right. Okay, so some variables here because we have quite a few. Okay, A, that is the current balance in the account. All right. P is the principal, and not Miss Claybaugh principal, but the starting amount. Okay. I think that principal is P-A-L, right? So principal, like she's your pal. All right, and then T is the time in years. R is the annual interest rate.
Sorry, I'm having trouble with the connection.
Would you shut up?
Thank you, Siri. All right, and then N is the number of times compounded per annum or per year, if you like. Okay. So you can kind of see here, the idea, right? So we're taking our amount of money that we kind of invest or, save, okay? We're going to multiply it repeatedly by that little interest rate, okay? But of course, it's not the straight up interest rate. We have to take that interest rate and divide by n. So the idea is, right, if you're compounding monthly, and let's just say you have a 2% interest rate, you don't get 2% every month. You get 1/12 of 2%, okay, every month. And so then over the span of the entire year, you end up getting that, quote unquote, 2% kind of thing, okay? So it divides up that 2% through the entire year, okay? And then it multiplies there. Yeah, repeatedly.
How much is a regular interest rate in banks nowadays? Is it 1.5%?
Yeah, I'd say less than that. I'd say less than even 1%. The problem, so what happens is the interest rates in banks are so low because the interest rates on loans are so low. So the banks aren't so happy to hold on to your money because they don't make as much money from loans. But if the loan rates go up, then the interest rates tend to go up too for the, and it's not necessarily a 1-to-1 ratio, but the idea is that the more money banks can make from loans, the more they want to entice other people to give them money to hold on to so that they can then give out more of those loans. So they give a higher interest rate for savings accounts and stuff like that. That's my understanding at least, but it's more complicated than that, I'm sure, but that's a basic idea.
And then investments and retirement accounts, a lot of those they're not always the same because it depends on
how they're invested, what kind of
whatever company is.
What kind of things you're investing in too. Yep. Mm-hmm. And of course, different people want to take different risks. If you're young, you can afford more risk and therefore potentially have more reward. if you're older, you don't want to potentially lose all your retirement, in a one bad day. So you put them in more, stable things. But yes, basic principles here. So anyway, compounding continuously. So this would be the situation where instead of getting a little hit every a discrete number of interest, interest hits or whatever, you have a continuous interest hit. So the idea is that every instant you're constantly getting an infinitesimal interest added to your account. I don't really know of situations where they use something like this, like savings accounts. No, they don't do that. So I'm not really sure where these kind of things occur, but there it is. Okay, and this can be for something like large populations of things too, like bacteria in a colony or something like that. You can even use something like the P to the RT. Even though bacteria are discrete, it's when there's so many of them, it eventually kind of has a very continuous kind of behavior. Okay, and again, the P is the same P as the principal here. R is the same R. It's interest rate. Oh, and I should put that it's interest rate as a decimal, by the way. Okay, so don't if it's 2%, don't put a 2 in there. It'll be, well, what is 2% as a decimal? Ooh, 0.02. Be careful. 0.2 is what percent? 20%. Yeah, be careful with that. Be careful. Anywho. Yep, so let's try some here. So number one, a total of $12,000 is invested at an annual percentage rate of 8.3%. Find the balance after 5 years if it is compounded quarterly, and then we'll also look at continuously. Okay, so let's just set this up here. So A equals, all right, P, our principal here, what is the starting amount? 12,000, okay, times 1 plus, all right, and then R, our interest rate here, is going to be what? Yeah, 0.083. So 0.083 over, and then N is the number of times compounded per year, right? So in this case, 4, right? Because it was quarterly. Okay, and then raised to the N again, so 4 times T, which is then, 5 in this case. Bless you, bless you. Okay. So, there it is. 12,000 times 1 plus 0.083 divided by 4 to the 4 times 5. At this point, is there any solving that needs to be done? You just multiply it all out. Okay, just type that in your calculator. Okay, and you can type it in one fell swoop if you like. Okay, please be careful with any intermediate rounding too. So, for example, if you're planning on typing this in pieces at a time, if you type in 1 plus 0.83 over 4. If you type this in and you say, let's make that 1.02, that's intermediate rounding because you still have to raise it to the 20th. You still have to multiply by 12,000. So don't do intermediate rounding. The best way, what's that? Exactly. You can just use the answer. Exactly right. Okay. Or if you want to store that, you can also. So there's a couple different ways you can do that, right? So for example, if I use second answer command, so second negative sign brings up that answer. So that will now reuse my previous answer wherever I want it in my equation. Alternatively, you can also press the STO button, S-T-O, and that'll take that answer that we just typed in and you can store it in for X. And now whenever I use X, it's that. And so I can do, what is E? Like the number E?
Yeah.
It's a number that's a constant that's used in exponential growth and stuff like that, basically.
No, I mean
the value, 2.7 something.
E times P-E-R-T.
Mm-hmm. E is a number, the number E. It's on your calculator.
E times P-E?
E to the RT. Yeah, it's P times E
okay.
raised to the RT.
E times, so I don't know why I drew that extra E there.
Okay, gotcha. So there is our final answer then, 18,095, and we're going to round, okay? So what? Nope, it's NT. N times T. That maybe looks like a plus sign there. I tried to put a little curly at the end. Okay, and so then approximately here, right, 18,095. And of course, since we're talking about money, we should probably round to just 3 decimal places. Okay, I will let you kind of choose how you want to round here, but I'll tell you right now that banks round down. Even if you have that 9 hundredths or 9 thousandths of a cent, bless you, they will not round up. They will round down. They get to keep that little fraction of a cent. Okay, and those things add up. Have you guys ever seen the movie Office Space? So that's kind of what they do. They developed this program or whatever to take the fractions of the cents off the transactions and stuff like that, and they end up making a lot of money doing that. I don't know if that's a true story or not, but anyway, it's interesting. Based on the number of transactions.
Do you want us to write like sentences for
No.
the answers?
No, you don't have to. If you want to, you can. But in this case, I think since it's just asking for a value, there's not a lot of interpretation that you have to do with this case. There are situations where you do need to interpret, but here I think it's just very straightforward. It's just like, that's the answer. That's the value. Okay? All right, continuously, then we're going to use the other formula. And by the way, these two formulas are, and I can't look it up. I will tell you guys later. I have to re-look now because I forgot. But I think I give you this one, but I think I give you this one too. I think they gave you both of these, but I'm not sure. So we'll come back to that. But I'm pretty sure you get both of these, for yourself. You, however, will be responsible for what all the variables mean. Okay? So while I will give you the formula, you will not know what these variables mean. I won't give it to you. You'll have to remember that. Okay? Anyway, PE to the RT, you get the idea there. Again, our principal is the same amount, 12,000. Okay, E to the R, 0.083, and then times T, 5. Okay, and so then we'll just type this in our calculator. Okay, the E button, there's two actually. If you press second ln, right, it's right there above the natural log, but there's also an E over here. If you do second divide by, that's just the number, the straight up number E, which is right by the pi there too. All right. And so we end up with 18,172.45. I will round, but again, banks don't. They don't want to give you any more money than they have to. Okay. And of course, situations like letter A, right, which I said I believe more closely match what you get at a bank at a savings account or something like that. Of course, in a bank, for a savings account, checking account definitely, you're going to be adding and subtracting money from those accounts, on a regular basis. So, it's rare that you just invest a certain quantity of money and never add or subtract from it, and then you can do this calculation. A place where that would happen if you have like a CD, a certificate of deposit, that's where you kind of like give some money to a bank, okay, and then you and you can't, I don't think you're allowed to add to CDs in general, and you definitely can't take out, or there's like a penalty or whatever kind of thing. And like you give it for like 2 years, and they give you like a slightly higher interest rate, kind of thing. Not that much enticing though, again, in a situation nowadays, but it's still a little bit more than nothing. Anyway, and so that would be a situation where you could maybe use that as a CD or something. All right, but the financial process is complicated, and I barely understand it, so maybe I'll just talk to someone like Miss Stieg, or I don't know, some business person. They might have a better idea about what's going on. All right, Miss Lemon maybe. All right, anyway, number 2, find the number of years required for a $3,000 investment to double at a 7% rate, compounded, and then we have 2 different scenarios here. Okay, so now we're doing a little bit different here. What variable are we going to be solving for here? T, right? Because we're supposed to find the number of years. So that means we're going to find T. Okay, we need to figure out what T is. So we should have then values for everything else. So let's see here. And again, we're doing it monthly, so we'll use the n times per year formula here. So we're taking our $3,000 investment, so that'll be 3,000. And 1 plus our interest rate. Well, what's R here in this case? 0.07 over, and then n is going to be what in this case? 12, right? Okay, and then what about t is what we're solving for, so it'll be to the 12t power. What are we going to equal though? 6,000, because we're asked when it will double. So we want to set that final amount equal to 6,000. So this is helpful too, right? Maybe you're like, I'd like to, save up money for a certain item. I want to see how long it'll take me to get to that item if I put this much in right now at a certain interest rate. There are also like tons of like online calculators for this kind of thing too, if you don't want to have to figure it out mathematically. But we're in a pre-calc class, so we're going to learn how to do it by hand, okay? But anyway, all right. So let's solve this thing. How should we proceed? What should be our first step here? Divide by 3,000. Wow, this is very similar to that problem that we had earlier. Not quite the same though. Okay. Whew. All right, we divided by 3,000 on both sides. Now what? Yeah, so yeah, we're going to continue to isolate here. Let's see. Do we get... Ugh, we do not. All right, so this is where things can get a little tricky in here. So this kind of like inside the parentheses here, sometimes you can end up with some like nasty decimals, right? So for example, if you put that all together, you end up with like 1.005833333333. My recommendation is either convert that to a fraction, okay, like this, 1207 over 1200, or you can just leave it as that form if you want to for right now, but eventually we're going to have to simplify it. So I'll go ahead and just simplify it here and just say it's 1207 over 1200. Okay, so we got to get that t out of the exponent. What can we use to do that? I just did 1 plus 0.07 divided by 12, and that simplifies to 1. It simplifies to that.
Take the root of t of both sides.
Not root of t. Nope.
Root of 12.
Nope. We could do that, but logarithms, right? You want to use a logarithm here. Use a log. It doesn't matter what base you use. So if you want to use like a common log, if you want to use log base 1207 over 1200, feel free. Okay. I'm not going to try and match my log base here just because I don't feel like writing a tiny, like a fraction so small and stuff like that. So what I'm going to do instead is just use like a common log. Let's just do that. So I'll say common log 2 equals, and then it'll be 12t log of 1,207 over 1,200, like this. Okay. So in this case, since I didn't match my log's base to my exponent's base, the logarithm does not just cancel out. Okay, I still have it there. That's a 12t. Sorry, I will try to write my t's more curly. Okay. And so then, for our final step here, what do we do? To get the t by itself, what do we do? Divide. Both by 12 and by the log of 1207 over 1200 there. Okay. So 12 log 1,207 over 1,200. Okay, so that cancels, that cancels. We have t is exactly log of 2 over 12 log 1207 over 1,200. Yes, Jeff?
Is it better to write your t's curly or with a long tail?
I don't know the difference. Like what? So what am I doing here?
They're making it curly.
Making it curly. Okay, and so.
As in, like, just instead of it being like twisted. Just
Oh, you're saying like this?
Yes.
Oh, I see. I don't know. Yeah, I think the curly makes it more distinct. That's my opinion, but you can do however you want. Okay. Wow. This number, though, is meaningless to us because we're looking for a number of time, and you never tell someone that, oh, yeah, I'll see you in like, log base 2 over 12 hours from now. You never say that, right? So we're going to type this into our calculator and get a decimal answer too. But again, why do we wait to do it until just now? Because anytime you round intermediately, you really lose accuracy. So you want to wait till the very end to round. Okay, this is a good exercise in being able to type things into your calculator accurately. So, approximately 9.93.
9.93, huh?
Okay.
That's monthly, right?
No, it was compounded monthly, but we're finding that t isn't in a number of years. Okay.
So yeah, 93 years.
Yep, 9.93 years. Right. All right, so you guys go ahead, do the continuously one. All right, so that's A equals P times E to the RT per. Okay. So go ahead and try that one. It won't be nearly as bad, I think.
So that's 6,000
How'd you type the last one in?
equals.
Like the whole thing, you mean?
Yeah.
So log of 2, close parenthesis, divide by, and then I opened a new parenthesis because it's the denominator. Okay. New parenthesis, and then 12 log, and then 1207 over 1200, close parenthesis.
Okay.
Will you expect us to find the decimal on the test, or can we just leave them?
Good question. So you want to just be able to say my answer is t equals this, and then put like years next to it or something like that?
Yeah, pretty much.
Like if we don't have a calculator?
Well, I mean, you'll have a calculator for that section. For anything like that, I expect you to simplify. I'll be okay with leaving it like that if you want. Yeah. Because in calculus, you would be able to stop right here, put years after it, and just say that's my answer. So, and this is pre-calculus, so sure, I don't have a problem with that.
2 equals.
Okay, so if you guys didn't catch on to that, just let me repeat that because Rohan, just maybe save some of you, or maybe this is interesting to you. If you choose, you don't need to give me the decimal answer there. You can just circle this answer and put years. So you can just circle the final kind of unsimplified thing, put the word years next to it, and then be done. That can be it. You don't have to simplify that as a decimal if you don't want to. But of course, multiple choice, Rohan, you need to be able to still do it potentially. So, okay. All right, sorry. Okay. But it is helpful for comparison's sake to actually get the decimals here, which I will be doing. Yes. 0.07, exactly right. Okay, good. Okay, Jen looking good there. Okay. Well, let's see here. I saw a lot of good things. All right. 9.902 is your final answer. So now in 1 and 2, okay, we had same situations. The only thing that was changed was how we were compounding, right? In A, we did quarterly, and then we compared that to continuously, right? So we held everything else equal. We compounded quarterly versus continuously. In number 2, same kind of idea. We held everything else equal. We compounded monthly versus compounding continuously, okay? And if you compare your answers here, what does it seem like in general is the better kind of compounding? Is monthly better or is continuously better? Or was quarterly better or was continuously better? So monthly, yeah. So if you look here, monthly takes a little bit longer to reach that goal of $6,000, whereas continuously it takes a shorter amount of time to reach that goal of $6,000. Same thing with investing for the same amount of time. If you compound continuously, you get a little bit more money than you would have if you had compounded quarterly. Okay, and that is kind of a general principle, right? The more compounding that you can have happen, the better. So, for example, semi-annually is better than annually. Monthly is better than semi-annually, right? Daily is better than monthly. So on and so forth. The more you compound per year, a little bit better it gets. Not much, but it's still better. But again, you don't really have choice sometimes. I guess you can maybe shop around and see other places that do it. But anyway, all right. Number 2, or the next section of problems we're going to look at here, are half-life problems. Okay, half-life problems, all right, which has to do with the decay of radioactive isotopes, I guess is what they'd be called, right?
First one.
So we'll get to that one. Hang on a second. Let me write the equation here. So there's other ways to write this half-life equation. For example, there's a way to come up with a half-life equation using E. All right, so if you go on to, I guess, do you guys learn that in chemistry, radioactive, like half-life and stuff like that in chemistry? Yes, no? Number 2, Mr. Thompson? Okay, okay, well, I don't know. I remember learning it in a science class when I was in high school. I don't remember what. Okay, but here is another version of the half-life formula that does not use E. It actually uses a 1/2, okay, to show that we're repeatedly, multiplying by 1/2 there. So A is the final amount of the radioactive material that's left. A sub 0, or A naught, N-O-U-G-H-T, I think, that is the initial amount. Okay, and so it's very common when you're dealing with a bunch of variables. If you see a variable with a sub 0 like this, that means it's a starting quantity. Okay, in calculus next year, if you decide to take it, you'll see like V sub 0 initial, or physics even, V sub 0 initial velocity, A sub 0 initial acceleration. You get the idea. P for I guess for amount. Yeah.
Does this equation also work for biological half-lives of medicines?
Yeah. I mean, it works for any half-life. Yes, any half-life.
Because it's not just radioactive things that have
Half-lives.
half-life. When you take a medicine, it goes by the same equation as it in going out of your body.
Okay.
That's why it takes quite a while to completely come down off of a medicine, so you don't really know what you're like when you don't take like a psychiatric medicine.
Yep.
Unless you're off it for weeks and weeks.
Gotcha. Because your body's still like getting ready to run.
The shorter a biological half-life, the harder the withdrawal is going to be.
Okay. Because your body has a tougher time adjusting or something like that, I guess. Interesting. Well, all of our examples here are going to be dealing with radioactive elements. Okay, so using this formula, right, the half-life of Widium is 40 years. If you have 6,000 grams now, how much will you have after 80 years? Well, this one we could probably do mentally, right? Because how many half-lives is 80 years for this Widium? It's 2 half-lives. So after 1 half-life, 6,000 will be what? 3,000. And then after 1 more half-life, 3,000 will be what?
1,500.
So the final answer here is, 1,500 grams. Okay? But of course, if you want to, we can also put that into our formula here. So 6,000 is our initial amount, times 1/2 to the, and then T is the amount of time it will be decaying, so that's 80 years. And then H, that's supposed to be an H, not an N there. H is 40 for the half-life of this particular element. Okay? And so again, you type that in your calculator, and you should end with 1,500. Okay? So that's the idea. Okay. Now, 135, this is where it gets a little bit trickier, because now 135 is not like an easy number of half-lives, right? You could do like 120, that'd be 3 half-lives, so 1/2 times 1/2 times 1/2.
That's 750.
So, for 135? Oh, if it was half and 1 more half, right? But this is 135, so we're gonna have to type this one. We're gonna do this one in our
That's
formula.
slightly less than
So we'll go back to the 6,000.
750.
We'll do 1/2 again, right? To the, and then again our T here is 135 over the half-life of 40. Okay, and again you type that whole mess in your calculator if you want to. Let's see, if you have the pretty type, it makes it even easier, but 6,000 parentheses 0.5 to the 135 over 40. Let's see my, there we go.
Why are we doing over 40?
Because, so 40 is the half-life of the element. So what you're basically doing here in the exponent is figuring out how many half-lives your element's going through, or your isotope, I guess, is going through over that 135 years. And then you raise it to that 1/2 power. So 578.329 approximately is going to be left. Okay, grams again. Okay. So why don't you guys go ahead and do the 400-year one. Okay. Now this one you could do without a calculator, because 400 is just 10 half-lives.
Yeah, but it gets really wonky.
It does get, the decimals get harder to do mentally, yes, for sure.
So that's
This formula, by the way, you will need to have in your brain. All right, I will not give you the half-life formula. Actually, maybe I do give it to you. Let me go check on that. Let me check. I'm thinking I might, actually. Now that I'm thinking. Okay. I will give you all the formulas, but I will not tell you what the variables mean. Okay? So you'll get all the formulas, but you will not know what the variables mean unless, of course, you know it, kind of thing. All right? I won't tell you what the variables mean, but I will give you the formulas. Okay? So that's what we'll say. Ugh. Okay. So, final answer here. Someone want to share what they get?
I'm not done yet.
Okay, Jeff's not done yet. Someone's finished? What we get? Natalie. 5.859. You got it. Okay. There it is. Questions on that?
Yeah, 5.85.
Good. And it'll be in grams, of course. Please do use units. So while I don't want a sentence, I do appreciate units. Please do make sure you use the units and stuff like that. All right, next. Population. Okay, this is what we've seen maybe in your population project so far. It's very simple. Y equals A times B to the X. That's what we're going to be using here. Okay. Whoops. I have a mistake here I have to fix. The population of Mathistan can be modeled by the equation y equals 2.056 times 1.002 to the, that should be an x, not a 2. Okay, where y is the population in millions and x is the year. So again, this is very similar to maybe how some of you have written your population equations, right? So just keep that in mind. Okay. So again, these are pretty easy questions here, and maybe I won't even bother like going through the rigmarole here. But what will the population be in 2010? So what should I do with that 2010? Where should it go? In for x, right? Because x is the year, so you just literally just do 2.056 times 1.002 to the 2010. No, x is just the straight up year. So whatever the year is, you just plug that in for x. So you don't have to like correct for like years since 2000 or something like that. But good question, because in some cases people are writing their equations like that. Okay, and if you do that, you should get approximately 114.063. And that number, 114.063, is a number of millions, very good, of people. Do not say this is a number of people, right? It's millions of people. How do we know?
0.63 of a person.
Population in millions. Well, sure. But if you multiply this number by a million, you'll have a whole number of people. But you're right, Jeff. No fractions of people. All right, letter B. If there were 111.81 million people in 2000, in what year will the population double in Mathistan? Okay, in what year will the population double in Mathistan? Okay, so 111.81 million people in 2000, in what year will the population double? So what should be our setup here? Okay, so the y would equal, right, so y is our population. What is our population goal here, though? Is it 111.81? No, it's double that, right? So we're going to put twice the 111.81, okay, in for y, and set that equal to 2.056 times 1.002 to the x, okay? So this is, again, very similar to the kind of calculations y'all have to do for your population projects, okay? So now we'll just solve this. So you can double the 111.81. We'll divide over the 2.056. Okay, we're going to get some, okay, here's what I'm going to do. I'll go ahead and double that, so Be careful with this intermediate rounding too. So I'll go ahead and say 223.62 over 2.056, and that's equal to 1.002 to the x. Okay, so I'm not going to simplify the 223.62 over 2.056 because it gives you like a really long decimal I don't want to have to write out. Okay, and then at this point, what should we use now to get that x out of the exponent? Log, right? And it doesn't matter what logarithm you use. If you want, you could do log base 1.002 of both sides. That's your choice. Or you can just use natural log, or you can use common log, whatever you want. Okay? I will match the base this time. I didn't do it last time. I'll do it this time. So I will say not natural log. Log base 1.002 of, bless you, 223.62 over the 2.056 equals, and then here I'll just say, well, that's just going to be x then. Okay. So in this case, I did match my base. You don't have to though. So for example, if you chose not to match your base here, I will go ahead and show that example as well. Let's say I just used like natural log. Okay, it'll be natural log of 223.62 over 2.056 equal to x times the natural log of 1.002, and then you just divide that natural log over. Kind of, my fat marker doesn't allow me to draw very.
Because the bases are the same, so it would just be the fraction divided by 1.202.
So if you're going to evaluate this in your calculator, you would need to either use the log base. Well, okay, I'm not sure I understand, but let me just say this. So if you're going to evaluate this in your calculator, either use the log base command where you would type in 1.002, and then here the 223.62 divided by 2.056. And you get 2346 approximately, or in the year 2346 maybe. Or you could do, again, the natural log here. So natural log 223.62 divided by,
It looks like it'd be more in the year 2347.
So right, the rounding is how you want to be careful with the rounding here. So you could say in the year 2346 or by the year 2347 kind of thing. Because 0.9 would mean we're not quite into 2347. We're almost there. It's like maybe November or December kind of thing. So, sure. Tommy?
You can't do that log-based formula if we have one of these calculators.
So you can. Do you have the log-based command? Like if you press the math button and you go down to the bottom of the math, do you have like log-based show up? Okay. So if you don't have that, but you chose to do it this way, you would evaluate using the change of base formula. So in other words, you would just do, you can use log or natural log. I'll just use log. You could do log of this. So log of that divided by log of the base. And it'll give you the same answer still. Okay? So, or natural log. You can use log or natural log, right? That's just change of base. All right. Any other questions on that stuff? So far, so good. I feel like I'm kind of speeding through things here because I know this stuff can take a while, and I want to try and give you guys ample time to work on the homework too. So, no questions? All right. Let's proceed here then. All right. So the last one is just something called I just call it percent increase or percent decrease, right? This is a simpler kind of exponential growth or exponential decay here, you might say. So we'll have a final amount, we'll have a starting amount, 1 plus r to the t. This is essentially the interest rate compounded per year, right? So we have the interest rate formula compounded n times per month. This is that formula if n is 1. So in other words, it's just once a year kind of thing, okay? So this is like a simpler version of that very first formula we saw.
It's like a hybrid.
A hybrid?
Yeah, of the other equation.
Yeah, they are all kind of related in a sense. Like I said, the half-life one can definitely be written as with e instead. I've seen it before, and so yeah, And this one is related as well to some previous stuff. So they're all kind of interrelated.
Not that people
Yes.
follow the dress code in school anyway, but is that a bottle of moonshine on your shirt?
No, it's just like a bell jar or whatever, like the canning jars. What you put inside the mason jar is up to you. But this is empty, so. All right, number 5, and that's on the record. All right, so anyway, number 5, you buy a house for $500,000 the week after you get married. The value of the house is set to decrease at a rate of 7.5 cents per year. How much is the house worth in 10 years or 20 years? Okay, so sadly, you probably wouldn't want to buy a house if that was the case, right? But anyway, let's see here. So our final amount, and we'll just do one of these because you get the idea. If you get the 10-year one, you'll understand the 20-year one. It's very similar. So what's our starting amount? A sub 0 is 500,000 times 1 plus our interest rate here. What should it be?
0.075.
Positive 0.075? Negative. Why negative?
Because it's shrinking.
We're decreasing. Right, we are decreasing. Sad face. Okay. So negative 0.075 raised to then the 10, right? Because it's 10 years. Okay, so there's our setup. And that you can just, type in your calculator. It's sad, yes, but it's true. I mean, it definitely happened, like in the... 2008. Yeah, and that like era of time right there when the economy was kind of shrinking and stuff like that.
If you let
Housing prices went down.
If you let the house get damaged and not put money into it.
Yep, that can also.
That would also reduce.
Absolutely.
The value.
Oh yeah, there's all sorts of.
End up with chip paint and grout missing, that sort of thing.
But the thing is, like, taking care of the house, that's within your control, right?
Yep.
Ideally, you should be able to control that stuff. But then when the whole economy is going poor, that's outside your control, and that's frustrating, of course, then, right? So, 229,291.17, we'll say. Okay, so 229,291.17.
That's not even half.
Yeah, sadly, yeah. And stuff like this did happen, for sure. I'm looking at houses, my wife and I are looking at potentially buying a house maybe next summer or something like that. And if you go to like Zillow or Redfin, you can see how like the value of the houses have changed like over time. Like if you look at a certain house, you can see like what it was selling for, whatever kind of thing in different years. And like there are houses that have definitely like halved in price since like 2006, 2007 when it was like peaked. When their prices were like peaked and stuff like that. So it's pretty crazy. Something to think about if you ever go to buy a house. Okay. But there's lots of things to think about when you buy a house. So anyway, 20 years, the difference is you just change that 10 to 20, so we'll forget about that. Number 6, though, the price of gasoline is set to increase at 3.5% per year. How many years will it take for the price to double? All right, so this one's interesting because what's our starting amount? We don't have one. But, right, do we need it?
No, we can just plug in anything.
Right, you can plug in anything you want to your starting amount because we then just want to see when it's going to double. So that's interesting, right? So if your gasoline starts at $5 a gallon and you want to then check when to see it's going to be $10 a gallon.
That is ridiculous.
Okay, I'm sure it's that place, it's that somewhere, But if you want to see that, right, it's the same as if your gasoline is $2 per gallon and you want to see when it's going to become $4 per gallon. So the idea of that doubling is going to take the same amount of time regardless of where you start. Okay. It's going to take the same amount of time to double. So we don't even need to put a number in. You could literally just say A sub 0 and then 2 A sub 0 there, if you want. All right, and then 1 plus 0.035 to the t, our unknown quantity. We're trying to solve for the time. So we can divide both sides by A sub 0. We're really just equal to 2 times 1.035. Equal to 1.035 to the t. All right, so just divide both sides by A sub 0 and get that. Okay, and at this point, logarithm will work, or
Just
natural log. We don't want to use a t root, no, because a t root we then wouldn't be able to evaluate because we don't know what t is still. So we want to use a log.
teeth root.
Yeah, exactly, a teeth root. Yes. Right. That's the dentist's favorite root. or the root canal, I guess, too. But all right, so there we go. So I'm going to use the same. I'm going to use matching logarithms here. So I'll match the base. So we have this.
At least Mr. Reed is funny.
Sometimes. All right, so approximately here, right, if we solve this, approximately 20.149, we'll say, years. Of course, life is not this simple, right? 20-some years from now, gas will not grow at a particular, interest rate, a certain, interest rate every kind of thing, every year or whatever.
The world's
It
supply
changes.
is basically just based on a few countries in the Middle East. However much they pump out of the ground is how much
They get to set the price, essentially, yeah, for the most part. Yep, you're right.
Of course, if other oil producing regions completely stop, like in the hurricane in Texas, that can also impact this.
Yeah, again, all sorts of things. And if you can be a person that can figure out how the market's going to move, you can make yourself a lot of money. But you also basically have to be psychic in order for that to happen. All right, last one here, number 7. The cost of a car 5 years ago was $10,000. It is currently on the market for $15,000. What is the rate of increase for the value of this car? So now, where do these numbers go? 10,000 is our what? Initial amount. Okay. 15,000 is our what? A, yes, our final amount. Okay. And let's see here. Well, 1 is still 1. We're solving for what variable here? R. We want to find the rate. Okay, so R is the interest rate we want. And then T, well, that is 5, right? Because it took 5 years for that $10,000 car to be valued at $15,000.
Wait, how does the price increase?
That's a good question. I was thinking that myself. And at least in a 5-year time span, probably not going to happen, right? In a 50-year time span, that could happen. But in a 5-year, probably not. Maybe, there you go. All right, divide both sides by 10,000. Sure, it could be inflation. That could be a thing, yeah. Something like that. The value of it's not the car's value that's increasing, it's the value of the dollar that's decreasing.
Maybe it's in Zimbabwe.
Maybe.
Yeah, a lot of those African countries have absolutely ridiculous inflation rates.
They can be, yes, exactly. It depends on their economies and things, yep. Okay. So we divide both sides by 10,000, we get 1.5 there. And now how should we solve? Logarithm? We don't need a logarithm, actually. We would do what, Natalie? Fifth root, because our variable is not in our exponent, so we don't need a logarithm to bring the variable out, okay? Our variable is in the parentheses, so we just fifth root both sides. All right? So, Jeff, you missed your chance there. This was the time where we do want to use the root, okay? So the fifth root of 1.5 is equal to 1 plus r, so r is precisely the fifth root of 1.5 minus r, minus 1, which... to do a fifth root in your calculator, there's a couple options. All right, option 1, bless you. What exponent is the fifth root equal to?
Caret -5.
Not -5. That'll be 1 over to the power of 5. 1/5 would be the exponent you want to use. Yep. So 1.5 to the 1/5 minus 1. Or you can also do an actual fifth root. If you press the math button and then you go down here to option 5, you need to type your root number in first. You have to type in the 5 and then go to that x root. So let me show you that here. So 5 math x root like that, and then you can type in the 1.5 and then the minus 1 like that, and you get the same thing. Okay. So approximately 0.08447, which as a percent is what? 8.447%. Okay. All right. Yes. Okay. If you guys are feeling good on this stuff, feel free to go ahead and get started on the problems over here for practice. Pick 6, okay? Or since I'm not checking homework, do as many as you want, all right? Or don't do any, but I suggest you work at least on a population project or something like that in the meantime, right? And it can't hurt to get some practice in there.
Where are these problems?
On the next page.
Okay.
All right, and then Jen will come answer your question.
I
Okay?
think I'll need to do more than 60 to get